All right, I'm sorry I couldn't be there today or for a little bit, but while I'm not there, I'm going to have you working on modern physics. Now, this is part of the curriculum, and typically we would cover it at the end of the year, close to the Regents exam, because it doesn't tie in super well to some of the stuff that we do throughout the year and isn't such a major topic. But I decided that I knew this was coming up, I didn't know when, and I would leave modern physics materials ready for you for when I'm not in school. So when you watch these videos, you should have this packet out with you. And it's all going to be about this essential question. What phenomena cannot be explained by classical physics and how can they be explained? So classical physics is going to be the kind of stuff that we spend most of the year talking about. And this is about stuff that can't be explained by it. So it's not so well connected to the rest of it. All right, so the first thing that we're going to do is we're going to talk about electromagnetic waves. So we have some background understanding of what an electromagnetic wave is before we go into modern physics and how we work with them. So electromagnetic waves are, the frequency of them is determined by the frequency of the source. So, but what are they? Electromagnetic waves are just anything on the electromagnetic spectrum. So that could be a variety of things. It could be light, it could be radio waves, it could be a variety of different things. We'll talk more about the spectrum later on, but for now, electromagnetic radiation is just anything on that spectrum. And one of the key features of it is everything on it is going to move at the speed of light. And because the speed of light is such a special quantity, it has a special symbol. And the symbol for it is c. And we can find the value from the front of our reference tables. So it's 3 times 10 to the 8th meters per second. And we'll go into this more when we talk about all kinds of waves, but waves have a certain equation where the speed of the wave is the frequency times the wavelength. And we can rewrite that in terms of electromagnetic waves to say that the speed of light is equal to the frequency of that ray or electromagnetic piece of information times the wavelength. And that's going to be a triangle equation. So you know we're going to make a triangle from it. And when we do that, we just cover up that c, which leaves v and lambda down here, and c up top. Do some example problems. It says to calculate the frequency, we have a wavelength of 3 times 10 to the 1 meters per second. Just to fill some stuff up here, c again means the speed of light, and f is frequency. And then that weird symbol is called a lambda, and that's our symbol for a quantity called wavelength, which is just another property of that electromagnetic wave. So we can come back down here, we're looking for the frequency, we have the wavelength as 3 times 10 to the first meters per second, and then the other thing I know is I know c because it's a radio wave, so that c of 3 times 10 to the 8th applies here. 3 times 10 to the 8th meters per second. And then I can use my triangle. So I have C, F, and lambda. And when I cover up F, I see that my F equation is F equals C divided by lambda. And I can substitute numbers into that equation. And when I punch that into a calculator, I get 1 times 10 to the 7. And then that's going, my meters are going to cancel out, and that's 1 over seconds, or our typical unit for frequency is actually going to be hertz. So 1 hertz, 1 HS is defined as 1 over seconds. So just something divided by seconds is equal to a hertz. We can keep going here. We're trying to calculate the frequency. We're given a wavelength there. So we have a wavelength of 5 times 10 to the negative 7 meters. We're looking for the frequency. And again, we have a light wave, so we know our C is 3 times 10 to the 8th meters per second. We can pull the same equation down here. frequency is c divided by lambda. We can substitute numbers into that. 3 times 10 to the 8th meters per second divided by 5 times 10 to the minus 7 meters, which comes out to 6 times 10 to the 14 hertz. Similar but different question here. We're looking for the wavelength and we're given a frequency, so we can start by saying we know the frequency is 1.5 times 10 to the 18 hertz. We still know that c is 3 times 10 to the 8th meters per second. Meters per second. And now we're looking for lambda. We don't want to come back to our triangle, but now we're going to want to cover up lambda instead of frequency. And we can see that our equation is going to be lambda equals c divided by f. And I can just substitute numbers into that equation. 3 times 10 to the 8th meters per second divided by 1.5 times 10 to the 18 hertz. And I get a wavelength of 2 times 10 to the minus 10 meters. And then on our last question, again, we're going to be looking for wavelength where we're starting with a frequency. So I can write the frequency is 5.8 times 10 to the 14 hertz. I have, again, c of 3 times 10 to the 8th meters per second, and I'm looking for the wavelength. So I can pull that same equation from up there and bring it down, where I am looking for wavelength, and I have c and frequency. I can plug those numbers in. 3 times 10 to the 8th meters per second divided by 5.8 times 10 to the 14 hertz, and I got 5.17 times 10 to the minus 7 meters. At this point, you should be able to move on to the practice on the next page. Thank you for tuning in, and I hope you're doing great without me.